Good afternoon, everyone. So what's better than one XKCD to start a presentation? Two XKCD, right. So this one is about de facto standard exchange data format. And I think we have one for scientific data, and that's HDF5. And it's much better engineered than a worksheet containing whatever photo you take from your screen. So I'm Samuel Debionne, and I'm with ESRF for about 4 years now. And with Alejandro and Laurent, who are hiding in the audience, we maintained the LImA code base, and we work on the next generation of acquisition library for 2D detectors. We call 2D LImA2. So with a lot of creativity. So the outline of this talk will be basically a feedback of our use case with 2D detectors data with LImA today, and what we plan to do with the next version we call distributed LImA2 soon. So first I will give you an overview about LImA. Switch to the next slide. Does it work? No? Yep. Okay, so LImA stands for Library for Image Acquisition. So it's a library for unified detectors control. It's for image acquisitions, 2D images, and processing as well. It's written in C++, and there is a Python binding available. And we have built a Tango device server on top of on that. It's open source, it's the GPL license, and you will find the GitHub link here and the documentation as well. And on the right side, you have a figure that shows basically the architecture of the whole thing. Starting from the bottom left, we have the detector SDK from the vendor, and we try to abstract the specificities and the peculiarities of the SDK with the hardware interface that every camera plugins have to implement. On top of this hardware interface, we have the control layer that manage the processing, the savings, eventually the frame accumulations and other image processings. And finally, we have the application. So the things have changed a lot since we started the project. And here you have the evolution of the data throughput of 2D detectors since 2005. So we are starting from 120 megabytes per second, and we are reaching 8 to 16 gigabytes per second with nowadays detectors. So it's more an explosion than an evolution, really exponential. We support over 30 detectors plugins for X-ray direct and indirect detection with different properties. They can be either photo counting devices or integrating devices, and they can work on X-ray or visible light. And LImA is used in many places all over the world, probably mostly in Synchrotron light sources. But so let's talk about HDF5. To emphasize here is the tensions between the producer and the consumer requirements. Effective, that means LImA. The first goal to achieve is data integrity. We don't want to lose anything. And we are working in a real-time context. We cannot buffer much of the data that are coming in. And so we need really good saving performance. In the other hand, the consumer perspective is they need to read the data often one or multiple times. They need good reading performance, and sometimes they need to read as we write. And that's where the swimmer comes in. On top of that, we have specific requirements depending on the techniques of the analysis. For tomography, we have high data rate, but also a read pattern which is quite orthogonal to the way we write the data. For XPCS, photon correlation spectroscopy, we also have high frame rate, but the low photo count is appropriate for sparse storage. And for macrocrystallography, serial macrocrystallography, we have a techniques that pre-process the data to find peaks, and that makes it also appropriate for sparse storage. The current implementation in LIMA is, I would say, pretty basic. We use the native HDF5. That means we write to file. Nothing fancy like John presented this morning. We are not using object storage or things like that. We chunk the data per frame, and it's not even configurable. We use the Direct DAQ API to bypass the data space and the filter pipelines, mostly for performance reasons. And that also enables the compressions of chunks in parallel. And we do that with, we use the LIMA thread pool for parallelizing the compression. And on top of that, we try to respect the Nexus conventions to some degree. With that, we can basically saturate the central storage bandwidth, which is not too bad, especially if we have chunks that are large enough. So the current system we have is a GPFS, IBM GPFS that supports a bandwidth of 2 gigabytes per second. And the network connection is a 20 gigabits Ethernet connection. The issues are not new. The first one is the global lock that we have at the library level. So we can only have one single effective write stream unless you remove the serialization, but that's something that's not really a good idea. We have always this corruption on crash, which is an issue because data integrity is our first goal. And it doesn't happen really often, to be honest, but when it happens, it's always a pity. And we use the direct chunk that we think is a kind of backdoor, and we would like something maybe better, just something more official in the future. So LIMA2 is the next iteration of LIMA. I already spoiled the bit. It's distributed, and the main reason is that we want a scalable system. Most of the detectors that we are integrating these days are modular. They are mosaics of tiled independent modules. They can scale up to 10 megapixels. We even have a Jungfrau that is 16 megapixel deployed, not at ESRF, but at XFEL, but we know that's coming. The acquisition frame rate is also increasing. We have detectors that goes up to 10 kilohertz. And so the data throughputs we expect is about 30 gigabytes per second. And in parallel, we also need to have a processing which is with low latency for multiple reasons. One is the on-the-fly image analysis for instance, for fast feedback, fast experiment feedbacks. Sometimes we want to adjust the experiments, the scans as it goes, depending on the chemical reaction we are measuring. And that requires the feedbacks of less than 10 milliseconds, say. And we also want to reduce the data online to reduce the throughput. The idea is to support multiple topologies depending on the detector's capacities. So for a basic module assembly, we would basically connect one that data acquisition computer per module. And each one will receive a partial frame. And all that needs to be reconstructed within the data acquisition mini cluster. Then we have the full frame dispatch, where the detectors implement features that we call the round robins. So the detector can send a full frame to multiple data acquisition computers in a sequence. And and we can also support another use case where we have, let's say, legacy detectors, but we want to distribute only the processing part. This is the third case on the right. I didn't mention that LImA2 is a library which is built on top of MPI. So we are building an MPI application in the end. So when we started LImA2, we started from scratch, and we decided to use the latest C++ standards, so C++17, which is available on many architecture platforms, etc. So we are looking for a modern C++ wrapper, and we discovered that there are plenty of them actually. We have of course, the one which is bundled with HDF5, and I'm not sure if it's deprecated. Maybe that's not not the case, but at least it doesn't support MPI, for instance, officially. Then we have the one from Steven Vargas. I don't know if he will be present his library in this meeting. We have another one from ESRF DMSC, H5XX, I5, that will be presented here tomorrow. And so in the end, we decided to go a much simpler way. We just basically use something that we call the unique handle and share handle, and just to manage the resource in a resource acquisition initialization way, AII. And this unique handle shared handle is modeled on the astute shared pointers. And then we use directly the C API. One of the reasons is that none of the wrapper here are covering the full C API. So I give an example of the usage of unique handle here. You have the base type, which is HIDT, and for file handler, you will pass the close functions that needs to be called whenever the resource is not used anymore, and you have predicate that tells if the handle is valid or not. In which case, here it's if the handle is negative, we know that the handle is not valid, and we don't need to call the close function. We have integrated HDF5 in 1 TBB. More specifically, we are using the flow graph part of 1 TBB. That one flow graph lets you express parallelism through graphs where basically nodes are chain. When a node receives a message, a new task is spawned and it executes the body of the node. Here I give you an example of the composite node that we have built for HDF5, made of a multifunction node responsible of the frame aggregation. And then we have the function node that compress the node for instance, in bit shuffle LZ4. And finally, we have the direct string saving. I present a small use case, which is the the one we are focused in right now, which is the serial microcrystallography use case. For this application, we use power noise, mostly because most of the processing is done on GPU. And this processing is basically specific to the detectors, which is a Jungfrau from PSI, which needs pedestal corrections and gain correction. And then we apply an algorithm which is the fast azimuthal integration to reduce the data and extract the peak or the background as you want. So on the top right you have an image of such application with many bright peaks. Probably this one is an accumulation actually, because there are so many bright peaks. And my point is how we store the data when they are sparsified. So there is no way, native way to save sparse data in HDF5. So we have kind of reinvented our own way of doing it. We basically use 3 data sets. One is basically the position of the pixel of the peaks in the image. Then we have the intensity. And to get in 3D, we have a frame pointer that tells wherever a frame starts. So that's the 3 data sets on the left. So far, we have been very conservative with our usage of HDF5, and I think it's really time for us to explore new features. We'll be really happy to try the multi-thread support that you are currently working on. But I don't know how it's specified right now, but it would be really great if we can provide our own executors, our own threads. We also would like to try the asynchronous API because blocking I/O wastes worker threads. Maybe that requires to move to a new virtual file driver or Vol. About sparse data, I think there is also work in progress now about that. So if there is any, we'll be interested. And I also would like to know how it works with compression and when it will be available. Regarding data aggregations, so we have data that comes from multiple processes, and sometimes we need to put them together, either using a virtual data set, or since we are running in the context of an MPI applications, we could also go with the parallel HDF5. And then again, how do we aggregate sparse data? That's an open question. For the applications that requires fast online analysis, we'll be interested in RMS because it will help in lowering the latency of online analysis. And we're also playing with GPU direct storage, since most of the processing is done on GPU these days. So to finish this, to close this this presentation, I'd like to open a discussion whether HDF5 should go one size fits all, or is it? Are we asking too much from HDF5? And I listed some inspiring technologies that are used in other facilities, like for RMS I already told about, HDFQL for metadata, or shall we use the query APIs from HDF5? ADIOS for flexible I/O. And for sparse data, we are looking at TileDB. And for time series data used by expressors, we know some facilities that use InfluxDB. So that's it. Yeah, there are many open questions here. Which one? No.
It rearranges data, and it does exactly what AGIOS does. It does stream data, and it works in parallel too.
Okay.
So, and it beats the speed of AGIOS for writing, and for reading it was about the same, but reading will be bad if you work with AGIOS anyway.
Okay.
But it's good to look into it. And there was something on the previous slide. Sorry, I forgot what it was. Are you aware of GPU Direct DAQ?
Yeah,
okay.
We looked at that, yes.
And there is no H5Q and H5X APIs. Yeah, they never made it to official library. Right?
Okay, they never made it? Okay.
Thanks. So there in the image of the file format that you were showing, so did I understand it correctly that you were supporting sparse data within HDF5 by actually making data sets of coordinates with the data?
Yep. That's where we store the sparse data nowadays.
And are you actually like linking these somehow together like as the dimension scales, or are these like normal data sets completely, like the coordinates, and you have just another layer on top of that that interprets them as coordinates? What I'm asking is really like whether in HDF5 you do have them as normal data sets completely.
Yeah, it's completely normal data sets.
Yes, okay.
So you need the application to know about that format to display them. And it's already integrated in FabIO. I don't know if it's...
I see. And one more question. So what made you actually choose like C++? So why are you actually doing it in C++? Is there some special reason, or was it just like that it was convenient?
One of the reasons is most of the SDKs are C or C++ SDKs. I think we have also much better control over memory allocation. I mean, if you are comparing to Python, for instance, multi-threading. We want the best performance, but also expressivity. So I think C++ was the best compromise between C, Python, C++.
Okay, thanks.
So you asked if the C++ wrappers are officially supported in the HDF5 library. They're not deprecated, but I would describe them as unloved. That they're still supported. We still maintain them, but we don't add a lot of features to them or actively develop them right now.